So generally speaking, okay, if you have a vector x, which is equal to x1, x2, x3, and so on up to xn, and you multiply it by a constant, kx, right, some scalar, well then the resulting vector is going to be kx1, kx2, kx3, and so on up to kxn. And the magnitude of kx bar is just going to be equal to k multiplied by the magnitude of x, sorry, not x bar, of vector x. Right? So that's multiplying a vector by a scalar. You can also multiply a vector by a vector. Okay? And there's different ways you can do this. Okay? You can multiply a vector by a vector and get another vector. This is a type of multiplication called the cross product. Or you can multiply a vector by another vector and get a scalar. And this is called the dot product. So in this video, we're just going to talk about the dot product. So if you have, say, vector x, right, is equal to x1 and x2, let's say we have two-dimensional space, and you have vector y, which is equal to y1 and y2, then x dot y, you could also write it as x1, x2, right, just the coordinates, dot y1, y2, well, that's going to be equal to x1, y1 plus x2, y2. You multiply each coordinate by its counterpart in the other vector, and you add up the results. Okay, so for example, let's say x equals 3, -1, and y equals 2 and 7. Okay, well, x dot y will be equal to 3, -1, dot 2, 7, which is going to be 3 times 2 plus -1 times 7. So that is 6 minus 7, which is equal to -1. It is a scalar value, right? You multiply two vectors in a way that gives you a scalar. And since multiplication and addition can be done in any order, the dot product can also be done in any order. So x dot y is equal to y dot x, okay, for any vectors x and y. Okay. Now, this example was in 2 dimensions. Generally speaking, if we were to write this for the general case, okay, x dot y is equal to x1 y1 plus x2 y2 plus x3 y3 plus and so on up to xn yn, where n is whatever number of dimensions you have. Okay? And if we want to write this using summation notation, well, for every single dimension from the first one to the last one, we multiply the x coordinate, well, that dimension's coordinate for vector x by that dimension's coordinate for vector y. And that's how we get the dot product. And remember, the result is not a vector, but it is a scalar. Now, there's a lot of applications to the dot product, both mathematical and in physics and engineering, and we'll touch up on all of that later on in a different video. What I want to show in this video is how that relates to linear equations. Okay, imagine an equation like this. Okay, vector 3, 7 with the dot product of vector x, y. And so here I'm going back to a more simple notation of using your x coordinate and your y coordinate in a Cartesian plane. Okay, so what would that be equal to? Well, you multiply the first coordinates, you multiply the second coordinates, you get 3x plus 7y. Okay. Now what if I were to write an equation like 3, 7 dot xy equals 5? Well, how would I rewrite that equation? Okay, so we have 3x plus 7y equals 5. Well, that's a linear equation. That's an equation of a line. We can rearrange this, right? We can rearrange it and have 7y equals 5 minus 3x, or y equals 5 minus 3x with everything divided by 7. Rearranging it further, y equals 5 over 7 minus 3x over 7. And now we have how we're used to seeing an equation of the line. Y equals negative 3/7 x plus 5/7, right? We have our slope, negative 3/7, and we have our y-intercept, 5 over 7. Right? That's how we're used to seeing the equation of a line. Right? And this equation here is the same as this equation here, and it's the same as this equation here. This is just three different ways of writing the exact same equation. And what is it an equation of? It is an equation of a line. Now what if we write something like this? Let's say 2, negative 1 dot xy equals 2, and 1, 4 dot xy equals negative 3. So we have two equations here. Okay, let's rewrite them in a way more familiar to us. So the first one here would be 2x plus negative y equals 2, right? There's our 2 times x, there's our negative 1 times y, negative y. And the second equation would be just 1x plus 4y equals negative 3, right? There's our 1x, and there's our 4 times y. Okay, and I'm going to simplify this. So 2x minus y equals 2, and x plus 4y equals negative 3. So now we have a system of linear equations. Right? We have two equations, two unknowns, x and y. If we want, we can rearrange this further. And our first equation would be 2x minus 2 equals y. Just switching the 2 and the y places. And we can have, for our second equation, 4y equals negative 3 minus x. And then if we divide, right, that's just moving the x over, right? And then we can divide everything by 4. We get y equals negative 3 over 4 minus x over 4. And writing that as an equation, two equations of lines, right? We have y equals 2x minus 2, and y equals a quarter x, negative quarter x, right, minus 3 over 4, right? And so if we solve for x and y in this situation, we will get the point where these two lines intersect. Okay, so this is an example of how using Cartesian coordinate system for vectors is very convenient, because, you know, for example, an equation of a line can be written as a dot product with one vector dot x and y equals something else. And later on, and this will be in other presentations, we'll talk about the equation of a plane in three-dimensional space, and intersections of planes and lines, and projections, and all that. That'll be discussed not in this video. What I want to get into is systems of linear equations. Okay? So let's say we have these two equations to solve. Okay? 2x minus y equals 2, and x plus 4y equals negative 3. Okay? So 2x minus y equals 2, x plus 4y equals negative 3. So a typical way of doing this, you isolate for y, which you can do here, right? And we already did that, right? We wrote y equals 2x minus 2, and then you plug that into the other equation, right? So x plus 4, and then instead of y, you write 2x minus 2, right? And then equals negative 3. And then we solve this, right? So x plus 4 times 2x is 8x. 4 times negative 2 is negative 8, equals negative 3. So we have 9x equals negative 3 plus 8, because we moved the 8 over to the other direction and combined the two x's. Okay? So then we have 9x equals 5, x equals 5 over 9. Okay? Then we have to plug that back into our equation for y. So we get y equals 2 times 5 over 9 minus 2. Okay? So we have 10 over 9 minus, let's call, instead of 2, 18 over 9. And so we have negative 8 over 9. Okay, so we finally have our solution. X equals 5 over 9, and y equals negative 8 over 9. Okay, so that's the standard way of solving it. We could have done things in a different order. We would get to the same answer, and that can be messy. And we're just working in two-dimensional space here. In 3 dimensions, 4 dimensions, things would be even messier. Now what we can do is something called matrix form. Okay, so these equations here, right? Notice that we have things arranged in certain columns. This column has what has to do with x. This column has what multiplies y, and this column has the constants. Okay? And recall that we can actually multiply equations by a constant. Right? So for example, x plus 4y equals negative 3. We can multiply everything by 2. 2x plus 8y equals negative 6. That would be true as well, right? It's an equation. Multiply both sides by the same number. The equality still holds, right? You can also subtract one equation from the other, or add one equation to another, okay? Because if let me just write things here, right? If this equals this, and this equals this, well, adding these two should give you the same result as adding these two, right? So you can add the two equations, and the result will also be true, right? So if you have 2x minus y plus x plus 4y, that should equal 2 minus 3. Okay? And that's another way to solve a system of equations. So let's do that. 2x minus y equals 2. I'm just going to rewrite it down here. (2x minus y equals 2) and x plus 4y equals negative 3. X plus 4y equals negative 3. Okay, so first let's multiply equation 2 by 2. Okay, so equation 2, we're going to multiply that by 2. And we get 2x plus 8y equals negative 6. That's our new equation 2. Our equation 1 is going to stay the same. 2x minus y equals 2. Okay. Now what we're going to do, we're going to take equation 2, okay, and we're going to subtract equation 1 from it. Okay. So again, our equation 1 stays the same. 2x minus y equals 2. But what's going to happen with our new equation 2? Well, 2x minus 2x is 0, right? So we have 0x. Okay. 8y minus negative y is actually going to be 9y, right? So plus 9y. And negative 6 minus 2 is going to be negative 8. So that becomes a negative 8. Okay. So just to repeat, equation 2 minus equation 1, 2x minus 2x, that's where our 0 comes from. 8y minus negative y, you're subtracting a negative, so you get another y, that's where our plus 9y comes from. And negative 6 minus 2, that's where our negative 8 comes from, right? When you're adding or subtracting equations, you have to group the variables, right? The x's stay together, the y's stay together, and the constant numbers stay together, right? You're adding the x's, you're adding or subtracting the y's, you're adding or subtracting the constants, right? So I'm going to write our equation 2 here a little bit more conveniently, right? Without that 0 there interfering with us. Okay, so we have 2x minus y equals 2, and then we have just 9y equals negative 8. Okay, and from this we can right away see, right, just divide with our equation 2 here, divide both sides by 9, and we get y equals negative 8 over 9. Done. We've solved for y. Okay, and then if we want, we can plug that into equation 1, right? So we have 2x minus negative 8 over 9 equals 2. Let's simplify that. 2x plus 8 over 9 equals 2. Let's give a common denominator everywhere, right? So 2x plus 8 over 9 equals 18 over 9. 2x equals 18 over 9 minus 8 over 9, just moving that constant to the other side there, that scalar to the other side there. So 2x equals 10 over 9, which gives us x equals 5 over 9. Okay, so x is 5 over 9, y is negative 8 over 9, which is the same result we got up here, but in a cleaner, more straightforward manner. Okay? Which is especially easier when you're working with more than 2 dimensions. But we're going to make it even cleaner, even easier. Okay? If we're always arranging things by columns, right? There's our x column, our y column, our just numerical column, right? And we're sticking with that, right? X column. And then here we're actually plugging things in, so we're dealing with just numbers without a y here. But up here, right, we still have, right, our x column, our y column, our numerical column. Well, why keep writing x and y and the equal sign, right? We can rewrite these equations in what is called matrix form, okay? So instead of 2x minus y equals 2, we're just going to write 2, oh, let me change the color here. We're just going to write 2 minus 1, and then a bar, and then 2. And then instead of x plus 4y equals negative 3, we're just going to write 1 for the 1x, and then a 4, and then a negative 3. 1, 4, negative 3. Okay? And this is our matrix. Okay? And we know in our heads that this column is the x's, and this column is the y's, and this is what it equals to. Okay, so that bar there, that just means what it equals to, right? So this is 2x minus y equals 2, and 1x plus 4y equals negative 3. And then we can do the same things that we did before, but it's less writing, it looks cleaner. So we're going to take our second row, right, which is like our second equation, and we're going to multiply it by 2. 2 times row 2. Okay? And what do we get? Well, the top is the same, and the bottom becomes 2, 8, negative 6. Okay? Very straightforward. So the next thing we're going to do is we're going to take our row 2 and we're going to subtract row 1. Okay, so row 1 stays the same, and then we subtract row 1 from row 2. So 2 minus 2 is 0, 8 minus negative 1 is 9, and negative 6 minus 2 is negative 8. Okay, and next we are going to divide row 2 by 9, right? Because we want a 1 in the bottom there, right? So row 2 divided by 9, so we have 2, negative 1, 2, and then we have 0 divided by 9 is 0, 9 divided by 9 is 1, negative 8 divided by 9 is negative 8 over 9. Okay, so this is called, this form of a matrix is called row echelon form. Okay, so you have, and we'll get into more detail later on about what row echelon form means, but essentially your leading number from the left, okay, has zeros in front of it as you move down, right? So if we had 3 dimensions, well then we would have, you know, some number and then a 0 and a 0 and say a 1 and a 0 and another 1 right there, and then some other numbers later on, right? So you have this triangle of zeros, loosely speaking. We'll give a more strict definition of row echelon form later on, okay? But essentially, you get it to a point where your bottom row, sometimes you might have a row of all zeros. So all of those go at the bottom, right? And then above that, your leading number only has zeros to the left of it, right? So in this case, in our bottommost row, our leading number only has zeros to the left of it, right? And then once you go a row up, you could have whole numbers later on, okay? But once we work in more dimensions, they'll also have zeros to the left of them. And in a more strict definition of row echelon form, the leading number is also a 1. Okay, so if we want to be more strict with row echelon form, we're also going to have to take row 1 and divide it by 2. Okay, so we have 1, negative 1 over 2, and 1. And then we have 0, 1, negative 8 over 9. Okay, so that's row echelon form. From that we know what y is, right? Because if you remember this column, this is the y column, right? So we know that y equals negative 8 over 9. Y equals negative 8 over 9. We can then plug it into our equation for x right at the top here, okay? Right? 2x minus y equals 2, just like we did right here. But we can also continue. We can continue working in matrix form, right? And get what is called reduced row echelon form. Okay, so with reduced row echelon form, you don't just have a diagonal of 1s and then 0s below it and to the left. You also have 0s above it and to the right. Okay, so here's how we would do that. Okay, so we want zeros up top here. So here it would actually be convenient to multiply row 1 by 2 again, right? So we're actually going to end up with what we had before we went to a more strict form of row echelon form. Okay, so it's actually the same thing we have up here, right? And we're going to say row 1 plus row 2. Okay, row 1 plus row 2, right? So 2 plus 0 is 2. Negative 1 plus 1 is 0, right? And 2 plus negative 8 over 9, well, let's just leave it at 2 plus negative 8 over 9. Okay, and this row here remains the same. Okay, and now let's simplify things a bit, right? 2, 0, 0, 1, and this 2 plus negative 8 over 9, well, that's 18 over 9 minus 8 over 9, right? And this is just negative 8 over 9. Okay, and we'll simplify things further. And again, all of these extra steps are not necessary when I'm talking about simplification. You could do it quicker, but I'm just showing it here so it's easier to follow, right? So we have 10 over 9, 0 and 1, and now we're going to divide our row 1 by 2. Right, so 2 divided by 2 is 1, 0 divided by 2 is 0. The bottom row stays the same. So that top row, 10 ninths divided by 2, well, that's going to be 5 ninths. Right? And so now, if we were to convert this to equation form, recalling that this is the x column, this is the y column, well, our answer is staring right at us. Right? 1x equals 5 over 9, and 1y equals negative 8 over 9. Solved. Okay, much cleaner solution. Here we have it from the very top to the very bottom. And recall, we did put in some extra steps for redundancy, so it's easier to follow. If we didn't do that, it would be an even quicker solution. And once you have 3 dimensions, 4 dimensions, it's much easier to solve systems of equations in this matrix form. And again, that final form where you just have 1s along the diagonal and 0s everywhere else, that's called reduced row echelon form. And we'll talk about more strict definitions of what row echelon form, reduced row echelon form is, and more complicated situations where you might have rows of zeros, where you might have non-square matrices. These are called square matrices because it's 2 by 2. The part of the matrix where we're talking about our variables. All those more complicated situations, we will get into that later on.